A planet made entirely of water and iron orbits perilously close to its star. The gravitational forces at play here can utterly reshape a world, and by the end of this, you will understand how these invisible pulls can both create hidden oceans and rip a planet to shreds. We will uncover how a global sea could hide a furnace of molten metal, and why such a world might one day stare at its sun with a single, liquid eye. What does it truly take for a planet to hold itself together? That gentle stretching we see in our own moon is a whisper of the cosmic shout that can reshape entire worlds. Tidal forces are not a single, uniform push or pull. They are a gradient, a difference in the strength of gravity from one side of an object to the other. Think of it like this: the side of a planet facing its star is tugged more powerfully than the side facing away. This difference, this imbalance of force, is what creates the stretch. It is a fundamental consequence of gravity, a principle laid out by Isaac Newton. The strength of this cosmic tug-of-war is not random. It hinges on a few critical factors. The mass of the star and the planet set the stage, but the real drama comes from distance. Move a planet closer to its star, and the gravitational difference between its near and far sides skyrockets. It is not just about being close, however. The very stuff a planet is made of, its physical character, determines how it will respond to this relentless pulling. A rigid, rocky world might resist, but a world with a fluid heart, a globe of water shrouding a core of iron, is profoundly vulnerable. This invisible gradient is the engine that can turn a serene, water-covered sphere into a geological pressure cooker, its internal fires stoked by an unending, asymmetrical pull. And this brings us directly to the unique and fragile world at the center of our mystery. This theoretical world is a study in extremes, a planet defined by just two primary ingredients. Its heart is a massive sphere of iron, a core that could be solid or churning with molten metal, containing a huge fraction of the planet's total mass. This is not a small metallic center like Earth's, but a dominant feature of the entire world. Surrounding this dense heart is not a rocky mantle like our own planet's, but an immense global ocean. This is not a shallow sea, but a layer of water hundreds of kilometers thick, a volume that dwarfs all of Earth's oceans combined. Under the colossal pressures within the planet, this water does not behave as it does on our surface. It can become a supercritical fluid, a strange state with properties of both a liquid and a gas, or it can be compressed into exotic, high-pressure forms of ice that remain solid even under scorching temperatures. How does such a place even come to be? Its origins likely lie far from its parent star, in the cold outer reaches of a young solar system where water ice was a plentiful building block. It is a world of fundamental physics, a simplified sphere of water and metal where the complex chemistry of rock is absent. This stark, two-part structure, with a fluid envelope wrapped around a dense core, creates the perfect conditions for tidal forces to work their dramatic and destructive magic. To see that magic in action, we must move this world from the quiet outskirts and into the stellar inferno. Its celestial path is the crucible where its destiny is forged. A planet's composition sets the stage, but its orbit writes the script. Two features of this orbital dance are absolutely critical: the distance from its star and the shape of its path. Picture a world huddled dangerously close to a dim red dwarf star, orbiting within what astronomers call the habitable zone, where temperatures might theoretically allow for liquid water. At this intimate distance, the difference in the star's gravitational pull on the near side versus the far side of the planet becomes immense. This is the first ingredient for disaster. The second is an orbit that is not a perfect circle but a stretched ellipse. This eccentric path means the planet's distance from its star constantly changes. At its closest approach, the periapsis, the star's gravitational grip tightens violently. As the planet swings to its farthest point, the apopsis, that grip relaxes. This is not a steady pull, but a rhythmic, pounding stress. The planet is stretched and then released over and over again with every single orbit. Imagine repeatedly bending a metal paperclip back and forth. At first, it just gets warm from the friction, but soon the metal weakens, it becomes fatigued, and eventually it snaps. This is exactly what happens to the planet's interior, but on a cosmic scale. This cyclic straining does not just create a little warmth, it pumps colossal amounts of energy directly into the planet's heart. For a world made of water and iron, this tidal heating process is a geological engine, one that can transform a silent, frozen sphere into a churning, molten pressure cooker. And the release of that pent-up energy is where the planet's true metamorphosis begins. This relentless gravitational kneading generates immense friction deep within the planet's structure. As the star's pull constantly deforms the global ocean and flexes the solid core, the resulting internal friction is converted directly into heat. For a world with a massive iron heart, this process is transformative. Tidal heating can pump enough energy into the core to keep it molten and churning for eons, far longer than its own primordial heat would allow. We see a smaller version of this in our own solar system with Jupiter's moon Io, a world so violently heated by tides that it becomes the most volcanically active body we know. But here the scale is planetary. A liquid, dynamo-active iron core creates a powerful side effect, a global magnetic field. This invisible shield could deflect the star's relentless radiation, potentially protecting a tenuous atmosphere or even exotic life forms dwelling in the dark, pressurized waters. Yet this internal furnace, born from orbital strain, does not stay quietly contained. The heat relentlessly generated at the core must travel outward, seeking an escape route through the planet's vast, watery shell. This journey of energy from the hot metal heart to the cold surface is where the planet's geology truly awakens. This internal heat must find a way out, and its escape carves the planet's face. With a furnace of molten iron at its heart and a thick, insulating shell of water and ice above, this world becomes a spectacle of cryovolcanism. Think of cryovolcanoes as geological vents, but instead of erupting with fiery lava, they blast forth plumes of water, slushy ices, ammonia, and methane. These are cold volcanoes driven by internal pressure rather than solely by heat. The tidal energy relentlessly generated in the core forces its way upward, melting pockets of the icy shell and seeking any weakness to reach the surface. When the pressure becomes too great, the planet's frozen crust fractures, and a geyser of volatile material erupts into the void. These eruptions constantly repave the landscape, creating a young and dynamic terrain of smooth, icy plains, bizarre frozen domes, and vast lakes of exotic compounds that flash freeze in the frigid vacuum of space. No mountain range or valley is permanent here. The ground you stand on one year could be buried under a fresh layer of cryogenic material the next, a surface in perpetual, churning renewal. This relentless geological activity is a direct gift, or perhaps a curse, from the tidal forces endlessly flexing the world. Yet the influence of this gravitational kneading reaches even further, shaping the planet's very structure in ways that defy simple imagination. Deep within this churning world, beneath the fractured ice and cryovolcanic plains, lies its third and most profound secret, the relentless tidal kneading does more than just heat the core and crack the surface. It likely sustains a vast, global ocean trapped between the frozen outer shell and the searing metal heart. Picture a subterranean abyss, a layer of liquid water dozens of kilometers deep, completely cut off from the sunlight and vacuum of space above. This is not a tranquil sea. It is a dark, pressurized realm kept warm by the constant energy pulsing from below, a world within a world. This hidden ocean becomes a crucible for chemistry. As the hot iron core interacts with the water above, minerals and chemical compounds continuously leach into the abyss. The very churning motion induced by the tides acts as a planetary scale mixer, stirring these nutrients throughout the entire watery volume. On our own planet, we have discovered entire ecosystems thriving in absolute darkness at the bottom of our oceans. They cluster around hydrothermal vents, where superheated, mineral-rich water erupts from the seafloor. These oases of life are powered not by the sun, but by chemosynthesis, the process of drawing energy from chemical reactions. The subsurface ocean of our tidal world offers an environment that is strikingly similar and potentially far more vast and stable. It possesses the three key ingredients thought necessary for life: liquid water, a rich supply of chemical nutrients, and a long-term, sustainable energy source provided by the tidal furnace at its core. This makes such bizarre water and iron worlds prime candidates in the search for life beyond Earth. They offer a paradox, a planet that may be geologically violent and frozen on the outside, yet harbor a warm, dark, and potentially living sea on the inside. Their habitability, however, hangs in a delicate balance. The same tidal forces that create and sustain this hidden ocean are also a constant threat. This cosmic braking system exacts a heavy toll on the planet's motion. The immense energy being converted into internal heat does not simply appear. It is slowly but relentlessly drained from the planet's own orbital and rotational momentum. Over millions of years, this energy transfer works to smooth out the planet's wild, elliptical path, forcing it into a near-perfect circle. At the same time, the planet's spin gradually slows, just as a spinning top eventually wobbles to a halt. The final stage of this process is tidal locking, a state where the planet's rotation perfectly matches its orbital period. One hemisphere, the day side, is permanently baked in the harsh, unfiltered light of its star. The opposite hemisphere, the night side, is condemned to an eternal, deep freeze under the cold blanket of space. This creates a world of two utterly different faces. The day side becomes a steamy cauldron where surface ice, if any remains, sublimates directly into a thin, vaporous atmosphere. The night side, meanwhile, is a frozen wasteland, so cold that even gases like nitrogen or carbon dioxide would freeze solid on the surface. This synchronization represents a kind of stability, a mature equilibrium in the gravitational relationship, but this stability for the orbit spells profound geological stress for the planet itself. The constant, one-sided pull from the star now never relents, forever deforming the world into a slight egg shape. This permanent tidal bulge places an unending strain on the planet's very structure, testing the limits of what water and iron can endure. This constant gravitational pull permanently warps the planet's very shape. It becomes a world stretched into a subtle oval with two bulges, one pointing directly toward the star and the other pointing directly away. The sides are perpetually squeezed inward. For a rigid, rocky world like Mercury, this effect is minimal, a slight distortion. But for our world of water and iron, with its liquid heart and pliable icy shell, the deformation is profound. The entire globe flexes, its solid surface rising and falling in a slow, ceaseless rhythm aligned with its orbit. This isn't a single event, it is the planet's permanent state of being, a figure held in gravitational tension. The stress this places on the brittle outer ice shell is unimaginable. It's like taking a hard-boiled egg and continuously pressing your thumbs into opposite sides. The shell would quickly develop a web of fine cracks. On a planetary scale, this creates a global network of fractures and faults, a spider web of weaknesses etched across the entire surface. These are not random scars, they are the direct fingerprints of tidal force, and they become the planet's most critical geological features. These deep-reaching cracks act as ready-made pipelines, connecting the warm, pressurized subsurface ocean directly to the frigid vacuum above. They are the channels through which the internal heat and cryovolcanic plumes can most easily escape, constantly venting the planet's inner energy and repaving its tortured landscape. This relentless deformation does more than just crack the surface. It fundamentally alters how the planet manages its internal furnace. The very act of flexing, of constantly reshaping billions of tons of rock and ice, generates additional friction and heat within the planet's body. This tidal heating supplements the energy already boiling from the core, effectively turning the entire world into a more efficient thermal engine. The planet's thermal evolution, the story of how it cools over billions of years, is now intrinsically linked to its orbital dance. It cannot cool down as long as it remains in this strained embrace, its internal fires stoked by the very forces that are tearing at its skin. This global network of fractures does far more than just scar the surface. It fundamentally alters the planet's thermal heartbeat. Imagine a vast, overheated engine. Without a radiator, it would quickly destroy itself. For our water and iron world, these deep-reaching tidal cracks become precisely that, a planetary-scale cooling system. They act as natural vents, or like the fins on a heat sink, creating direct pathways for the immense warmth generated in the core and the subsurface ocean to escape into the frigid vacuum of space. Warm, chemically rich water from the hidden sea can well up through these faults, reaching the surface where its thermal energy radiates away. This process is astonishingly efficient, turning the planet's entire tortured crust into a giant thermal regulator. This creates a remarkable and delicate feedback loop, a self-correcting mechanism written in gravity and ice. Intense tidal heating leads to more flexing and more global fracturing. More fracturing, in turn, creates more of these cooling vents, which allows the planet to shed its internal heat more effectively. This increased cooling prevents the subsurface ocean from overheating and boiling away, or from melting the icy shell entirely. Conversely, if tidal forces were to weaken, the fracturing would lessen, the cooling would become less efficient, and the internal heat would begin to build back up. It is a natural thermostat, one that maintains a precarious equilibrium. The tidal forces, seemingly so destructive, are also the very thing that prevents total catastrophe. They stop the world from either freezing solid into a silent, icy billiard ball, or from erupting into a permanent, steam-shrouded inferno. This delicate thermal balance is the key to the world's long-term stability, allowing its hidden ocean to potentially persist for billions of years. But this entire beautiful, fragile system rests on a knife's edge. What happens when the gravitational forces become too extreme, when this self-regulation fails? This ultimate disruption has a name, the Roche limit. It is the point of no return in a planet's orbital decay, the exact distance where a star's tidal forces exceed the planet's own gravitational self-control. For our water and iron world, crossing this threshold would be a death sentence. The star's gravity would begin pulling harder on the planet's near side than on its far side, and this difference would finally overcome the bonds holding the world together. The destruction would be methodical and terrifying. the vast global ocean, the least gravitationally bound part of the planet, would be the first to go. Billions of tons of water and exotic ice would be ripped from the surface, shredded into a colossal, swirling ring of vapor and ice crystals that would slowly spiral inward toward the star. This would leave behind the planet's naked, battered iron core exposed to the vacuum, but its reprieve would be brief. Even this dense metallic heart is not immune. The same relentless tidal forces would continue their work, stretching and compressing the core until it, too, began to fracture and disintegrate, its molten innards spilling out into the void. The entire planet would be systematically dismantled, transformed from a world into a cloud of debris. Astronomers have observed telltale signs of such cosmic violence around other stars, disks of material unusually rich in metals and minerals. These could be the grave sites of entire planets, the final, glittering remnants of worlds that ventured too close to their suns. This is the most extreme expression of tidal power, the complete and utter annihilation of a celestial body. Yet not every world meets such a violent end. Many settle into a tense, lasting stalemate with gravity. That single, staring eye of open water is the final, breathtaking transformation. This is the eyeball planet, a world locked in a permanent gaze with its star. On the blistering dayside, the relentless stellar radiation beats down, melting a circular cap of the icy shell to create a lone, liquid sea. This is the planet's pupil, a single ocean of open water surrounded by an immense frozen sclera that stretches across the entire globe. The rest of the world, from the frigid night side to the vast twilight ring in between, remains encased in eternal ice. But this is not a cold, dead eye. The tidal forces we have followed, the very same ones that fracture the crust and heat the core, provide a vital spark of life. They pump geothermal warmth upward from the planet's molten heart, ensuring this lone ocean never completely freezes over. Even on the dark side, that internal furnace keeps the subsurface ocean liquid, a hidden warmth beneath a frozen sky. The stability of this bizarre configuration is a perfect balance. Solar energy melts the ice from above, while tidal energy prevents a deep freeze from below. The result is a stable, localized sea in the most unlikely of places, a single, persistent puddle on a planet-wide scale. The climate within this isolated marine environment would be unlike anything in our solar system. Constant, searing starlight bathes the liquid pupil, while just beyond its shores, temperatures plummet to depths that make Antarctica seem temperate. This sharp divide could whip up permanent, violent storms along the ocean's icy rim, a never-ending tempest where warm, moist air from the open water slams into the cold dome over the ice. The chemistry in this lone sea would be equally strange. Minerals and nutrients churned up from the deep by the same tidal forces that heat the core would be concentrated here, creating a potent, self-contained chemical broth. It is a crucible, a bizarre and isolated laboratory for probiotic chemistry, all held in the planet's unblinking eye. This internal churning challenges the very idea of a simple, layered world. One might assume a planet made of water and iron would naturally settle, with the heavy metal core sinking to the center and the lighter water floating above in a neat, stable shell. Yet the intense, rhythmic kneading of tidal forces can violently upset this order. Think of stirring a cup of tea with a dense syrup at the bottom. The spoon's motion creates swirling currents that mix the layers together. On a planetary scale, the tidal flexing acts as that cosmic spoon. If the heating is powerful enough, it can drive colossal convection currents throughout the immense water mantle. These are not gentle flows but planet-spanning upheavals, powerful enough to prevent the formation of distinct, stable layers of high-pressure ice. and potentially even strong enough to drag blobs of dense, molten iron upward from the core, mixing the planet's fundamental ingredients. Conversely, if the tidal forces were to lessen, or if the planet's orbit circularized and its internal furnace began to cool, this violent churning would gradually subside. Without that constant stirring, the planet's interior would finally achieve the separation it was denied. Exotic forms of ice, like Ice 6 or Ice 7, which remain solid under crushing pressures and high temperatures, could crystallize into vast, stable layers between the liquid ocean and the metallic heart. The world would transform from a homogeneous mix into a complex, stratified sphere, an onion-like interior with a metal core, a mantle of successive high-pressure ice layers, and finally a global ocean capped by a frozen crust. Tides, therefore, act as the master controller of the planet's internal architecture. They determine whether the world is a churning, mixed cauldron or a neatly layered, differentiated orb. This fundamental structural choice has a direct and powerful impact on the planet's magnetic personality. A churning, molten iron core is the engine for a global magnetic field, but if that core is constantly being disturbed and mixed with overlying material, the dynamo effect could be weakened or even stilled. A planet with a stable, layered interior might maintain a stronger, more consistent magnetic shield. The invisible hand of gravity, pulling and squeezing from afar, writes the blueprint for the world's very heart, deciding its structure and its power to protect itself from the cosmos. A magnetic field is the planet's invisible suit of armor. This protective bubble is woven from the motion of its molten iron heart, a process known as the dynamo effect. Picture the churning, liquid metal of the core as a vast, spinning conductor. As it rotates and convects, it generates powerful electrical currents, and these currents, in turn, create a global magnetic field that stretches far out into space. For this to work, the core cannot be a silent, solid sphere. It must be a vigorously active, liquid dynamo. This is where tidal heating proves absolutely vital. The relentless gravitational kneading pumps energy directly into the core, keeping it molten and violently churning for billions of years, long after its initial heat from formation would have faded. Without this constant tidal stoking, the iron heart could cool and solidify, and the planetary dynamo would sputter and die. A tidally heated water and iron world is therefore perfectly primed to sustain a powerful, global magnetosphere across geological ages. This magnetic shield is not a mere curiosity. For a planet huddled close to a tempestuous red dwarf star, it is a matter of survival. Such stars are notorious for their fierce stellar winds and violent radiation flares. Without a magnetic field, these relentless attacks would slowly but surely strip away any atmosphere, blasting the air molecules off into space. The magnetosphere acts as a deflector shield, bending the flow of charged particles around the planet and safeguarding the delicate envelope of gases that might cling to its surface. This protection extends down to the ground and even deeper. It helps shield the surface from harmful radiation that could break apart complex molecules, and it may even help protect the chemistry brewing within the subsurface ocean. The presence of a strong magnetic field, therefore, transforms this world from a vulnerable target into a fortified sanctuary. Its strength is a direct gift from the orbital forces that strain it. Now consider what kind of atmosphere could survive under such a guarded sky. The very air this world breathes is forged in its fractured heart. Cryovolcanos are more than just geological curiosities. They act as a global atmosphere factory, tirelessly pumping water vapor, nitrogen, methane, and other volatile gases from the warm interior out into the void. Each eruption is a gasp, a contribution to a tenuous shroud that could wrap the entire planet. Over eons, this constant outgassing might build a substantial atmosphere, one thick enough to support clouds, weather patterns, and even precipitation, a faint echo of the cycles that shape our own world. Yet this fragile blanket of air is under perpetual siege. The planet's intimate dance with its star comes with a terrible price. Bathed in intense ultraviolet radiation and battered by the relentless stellar wind, the upper layers of the atmosphere are constantly being blasted away into space. This creates a dramatic tug of war between the planet's internal forces and the star's external violence. The atmosphere exists in a precarious dynamic equilibrium. Cryovolcanism from below struggles to replenish the losses, while stellar activity from above works tirelessly to strip it bare. The very thickness of the air, its pressure and composition, becomes a live readout of this conflict. A period of intense tidal heating and rampant cryovolcanism might lead to a thicker, denser atmosphere. A lull in internal activity or a particularly violent stellar flare could cause it to thin dramatically. This balance is not just about quantity, but also about character. Lighter gases like hydrogen and helium are the easiest to strip away, while heavier molecules like water vapor or carbon dioxide might persist longer, potentially creating an atmosphere strangely enriched in certain elements. The fate of the water itself, the world's primary ingredient, hangs in this same delicate balance. The fate of the water itself is written in the light of its star. High in the planet's atmosphere, especially over the scorching day side, individual water molecules drift into a zone of peril. Here, they are bombarded by high-energy photons, packets of raw stellar power. When one of these photons strikes a water molecule, it can shatter it, breaking the bonds that hold it together in a process called photodissociation. The water is literally torn apart, its hydrogen and oxygen atoms sent flying on separate paths. This is where the planet's greatest treasure begins to bleed away into the void. The liberated hydrogen, being the lightest of all elements, is incredibly agile. With just a little energy, it can achieve escape velocity, flinging itself away from the planet's gravity forever, lost to the interstellar winds. The heavier oxygen often remains behind, but it is a hollow victory. Without its hydrogen partner, it cannot reform into life-sustaining water. This is a slow, silent robbery, a trickle of hydrogen escaping with every passing moment. Over billions of years, this constant leakage could drain a global ocean. A world born of water might slowly transform into a dry, icy husk, its surface frozen solid as its atmosphere thins. If the process continues to its ultimate conclusion, the entire watery mantle could be stripped away, leaving nothing but the naked, glowing iron core exposed to the heavens. The cruel irony is that the planet's own internal furnace, its tidal heating, actively accelerates this disaster. By driving relentless cryovolcanism, it pumps a continuous supply of fresh water vapor into the upper atmosphere, constantly feeding new fuel to the photodissociation process. The very forces that sustain a hidden ocean are also, slowly but surely, helping to desiccate the entire world. This represents the final, inexorable change to the planet's fundamental character, a transformation from a water-rich sphere to a barren relic. Could we ever hope to see such a world in its death throes, to witness this cosmic water loss in action? That faint, unexpected warmth is the ghost in the machine, a whisper of the planet's inner fire. Astronomers hunting for such a world from light years away would be detectives searching for these subtle, telltale clues. The first step is finding the world at all, often done through the transit method. As the planet passes in front of its star from our vantage point, it causes a tiny, periodic dip in the star's brightness. This reveals the planet's orbital period and its physical size. But size alone does not tell the story of a water and iron globe. The next piece of the puzzle comes from measuring the planet's mass, often through a different technique that watches the star wobble under the planet's gravitational pull. Combining the size and the mass gives us the world's average density. A planet with the radius of Earth but a significantly lower density cannot be a rocky world like our own. It must be made of lighter stuff, pointing directly towards a composition dominated by water or other volatiles, a global ocean wrapped around a dense core. Yet this still only describes a static, silent sphere. To see the tidal forces at work, we must look for the planet's heat signature. When astronomers point their infrared telescopes at this distant world, they would find something peculiar. The planet would be glowing with more thermal energy than it receives from its star. This energy imbalance is the smoking gun. It means the planet has an internal heat source, a furnace burning deep within. For a small, tightly orbiting world, this excess infrared radiation is the direct and unmistakable signature of tidal heating. It is the waste heat from all that gravitational kneading, finally radiating out into the cold of space. The combination of a low density, suggesting a watery composition, and a powerful infrared glow, betraying intense internal activity, would paint a compelling picture of a world actively being sculpted by the invisible hand of gravity. We do not have to look to the distant stars to find a laboratory for this process. Our own solar system holds a perfect, albeit smaller, analogue. Europa is a world that proves our theories are not just mathematical abstractions. Orbiting the giant planet Jupiter, this enigmatic moon is a frozen sphere with a secret. Beneath its cracked, icy crust lies a global, salty ocean, kept liquid not by the distant sun, but by the immense tidal forces Jupiter exerts. Its surface is a tapestry of fractures and ridges, a direct mirror of the gravitational stresses constantly flexing its interior. We have even witnessed plumes of water vapor erupting from its south pole, a spectacular confirmation that its hidden sea interacts with the surface. Europa is not alone. Saturn's moon Enceladus performs a similar, breathtaking act, spraying its subsurface ocean directly into space from geysers at its southern pole. And Ganymede, another of Jupiter's large moons, likely possesses a layered ocean trapped between different phases of ice. These are not dead, frozen rocks. They are active, dynamic worlds, and the engine for all this activity is tidal heating. The gravitational pull from their massive parent planets, combined with subtle orbital dances with neighboring moons, stretches and squeezes their interiors. This constant kneading generates enough internal friction to melt ice on a planetary scale, creating and sustaining these vast, dark seas. For scientists trying to understand a hypothetical water and iron exoplanet, these icy moons are invaluable natural laboratories. We can observe their cracked surfaces and measure their heat output, testing our predictions about how tidal forces fracture an icy shell and power a geological system. The plumes from Enceladus allow us to directly sample the chemistry of a subsurface ocean from orbit, giving us clues about the nutrient richness and potential habitability of such enclosed environments. Every new observation from these moons refines our models, helping us paint a more accurate and vivid picture of what a larger, more extreme version of this world might be like. Our own solar system provides the crucial ground truth for exploring the strange physics of distant exoplanets. With these lessons in hand, we are ready to contemplate the ultimate expression of these forces, a world pushed beyond any equilibrium into a state of constant, glorious upheaval. This steam world is the ultimate pressure cooker, a planetary state of matter pushed beyond familiar limits. When the tidal furnace within rages out of control, the delicate thermal balance shatters. The internal heat flux soars, overwhelming the icy crust's ability to radiate that energy away. It is no longer a gentle warming, it is a planetary-scale boil. The immense global ocean, once liquid or frozen, cannot remain stable. The entire water envelope begins to vaporize, not just at the surface, but from the deepest abyss upward. The planet undergoes a violent phase transition, shedding its identity as a world of seas and ice. What emerges is a seething sphere of supercritical steam, a thick, dense atmosphere that extends all the way down to the iron core. The core itself now sits at the bottom of this gaseous ocean, a dark metallic sphere bathed in unimaginable pressure and scorching heat. At this profound boundary, where molten iron meets a supercritical fluid, chemistry itself is forced into strange new behaviors. Exotic compounds could form and dissolve in the intense conditions, an alchemy never seen on any conventional world. This steam world represents a radically different evolutionary endpoint, a destination dictated solely by the ferocity of the tidal forces at play. It is a world where the familiar states of solid, liquid, and gas are transcended, replaced by a single, seething, fluid sphere. This dramatic transformation begs a deeper question, one that reaches across cosmic time. What if the planet's orbit is not a permanent sentence, but a variable in a much longer story? The journey to this stellar forge is not always a direct one. A planet's orbit is not a fixed path carved in stone, but a dynamic trail that can shift over millions of years. This process, known as orbital migration, can completely rewrite a world's destiny. Picture a water and iron planet forming peacefully in the cold, dark outskirts of its solar system, a frozen sphere with a silent, slumbering core. Then, a gravitational nudge, perhaps from a swirling protoplanetary disk or a close encounter with a sibling planet, sets it on a slow, inward spiral. As it drifts closer and closer to its star, the gentle tidal forces it once experienced transform into a crushing embrace. The delayed reaction is spectacular. A world that was once a dormant ice ball suddenly awakens. Its internal furnace, stoked by the new, intense gravitational kneading, roars to life. The ice shell, once frozen solid to its very foundation, begins to melt from the inside out, creating a churning subsurface ocean where none existed before. This is a planetary puberty triggered by a change of address, a second birth fueled by gravity itself. The reverse is equally dramatic. A planet migrating outward would feel its tidal fires slowly die, its internal heat fading as the gravitational pull weakens. Its oceans would freeze from the core outward, layer by layer, until the entire world became a single, silent block of ice. This means that to truly understand such a world, we cannot just look at its current orbit. We must read its entire dynamical history, the epic migration that brought it to its present location. This adds a profound layer of complexity to the question of habitability. A planet in the so-called habitable zone today might have been a scorched wasteland in the past or a frozen tomb. Its potential for life depends not just on where it is, but on the path it took to get there. The scale of this planetary drama is also dictated by its sheer physical size. The planet's own mass is a shield against the stellar tide. A world with more bulk possesses a stronger gravitational pull of its own, an internal force of cohesion that resists the star's attempts to stretch it. Think of a dense, heavy rubber ball compared to a light, airy sponge. You can squeeze and deform the sponge with ease, but the solid ball will barely budge. This is the fundamental difference between a high-mass and a low-mass water and iron planet. A more massive version of our world would be a compact, tightly bound sphere where the immense pressure crushes the water into exotic, high-pressure ices, creating a rigid interior that is difficult for tidal forces to flex. Such a planet would experience far less internal heating and would be far more resilient, perhaps never even approaching the brink of disruption. its story would be one of geological quiet. In stark contrast, a lower mass planet with the same watery composition would be a pliable, vulnerable world. Its weaker self-gravity cannot hold its structure as firmly, making it exquisitely sensitive to the star's gravitational pulls. It would deform easily, heating up like clay in a potter's hands, its orbit decaying faster, and its fate swinging wildly based on the slightest orbital nudge. This relationship between mass and radius is the key that unlocks a distant world's internal secrets from light years away. When astronomers combine transit data, which gives a planet's size, with radial velocity measurements, which reveal its mass, they calculate its average density. A planet with the mass of Earth but a significantly larger radius must be made of lighter materials. It cannot be a rocky world like our own. That low density is the primary clue pointing to a global ocean or a massive, icy mantle enveloping a dense core. But the detective work goes even deeper. By comparing the precise radius to sophisticated planetary models, scientists can start to discriminate between a planet that is mostly solid high-pressure ice, one with a deep liquid ocean beneath a thin crust, or one that has been heated so violently it has become a steam world shrouded in a thick, extended atmosphere. Each of these states would present a different face to the cosmos, a different radius for the same mass, betraying its internal condition. The strength of the tidal forces it experiences is written directly in this fundamental physical relationship. This entire structural drama, however, hinges on the behavior of the most common molecule in the universe, one we often take for granted. The physics of water itself under such extremes is anything but simple. Deep within the abyss of a massive water world, the rules of physics no longer apply. The crushing pressure from hundreds of kilometers of overlying water forces the molecules into exotic crystalline prisons. This is the realm of high-pressure ices, forms of water with names like Ice 6 and Ice 7. Unlike the fluffy snow in your freezer, these ices are denser than liquid water, meaning they would sink like a stone in any earthly ocean. In a large enough world, this dense ice does not just form at the bottom, it crystallizes into a solid layer, a thick mantle of exotic ice separating the familiar upper ocean from the planet's metallic heart. The boundary between the liquid sea and this solid ice mantle is not a sharp line, but a gradual, slushy transition zone tens of kilometers thick, a strange frontier where water is neither fully liquid nor fully solid. This internal architecture creates a world with not one, but potentially two distinct oceans. The relentless tidal heating we have followed can melt the base of this high-pressure ice layer, right where it meets the hot iron core. This carves out a second, deeper ocean, completely isolated from the one above, a dark sea trapped between a ceiling and a floor of solid ice. The planet's interior becomes a complex, layered sphere, a labyrinth of phase changes where the very state of matter shifts with depth. The tidal forces constantly flexing this world now have a new and rigid material to work on. As the gravitational pull stretches and squeezes the entire planet, these thick, solid ice layers bend and grind against each other. This is not a gentle motion, it is a colossal friction, generating immense heat directly within the ice itself. This internal friction becomes a major contributor to the planet's energy budget, a secondary furnace burning within its frozen mantle. This entire intricate structure, from the depth of the upper ocean to the existence of the lower sea, is held in a delicate balance by the planet's rotation. The relentless tidal tug works to slow the world's spin, gradually lengthening its day. A faster rotation creates stronger centrifugal forces that can slightly change the planet's internal pressure profile, potentially thinning the high-pressure ice layers. A slower, tidally locked rotation allows for a thicker, more stable and complexly layered interior. The very length of a day on this alien world is not an accident of its birth, but a direct consequence of the gravitational forces that continually sculpt its hidden heart. That initial, furious spin was a gift from its violent birth. The planet formed from a swirling disk of gas, ice, and metal, and all that colliding, accreting material imparted a tremendous rotational momentum, spinning the newborn world like a top. In its youth, its day might have lasted only a handful of hours, a dizzying cycle of light and dark, but this rapid spin was destined to slow. The same tidal forces that heat its core and fracture its crust also act as an immense and relentless brake, applying a constant torque that saps the planet's rotational energy. The efficiency of this braking system depends entirely on the world's pliability. A rigid, rocky planet would resist, its spin fading slowly over many billions of years. But our world, with its vast fluid ocean and deformable structure, is profoundly susceptible. It offers little resistance to the star's gravitational grip, allowing its rotation to be steadily wrung out of it. We can trace this planetary life story in the lengthening of its day, a chronology written not in rock, but in the gradual stillness of its spin. Over hundreds of millions of years, the frantic pace of its youth gave way to a slower, more stately rotation. The days grew longer, the cycles of stellar heating and cooling stretched out, fundamentally altering global weather patterns and ocean currents. This deceleration was a slow march toward a final, fixed state. The end point of this process is the tidally locked configuration we see today, one face forever scorched, the other frozen in endless night. But this locked state is not the whole story. It is merely the final, stable chapter in a long and dynamic history of a world gradually being brought to a halt by the star it orbits. This final locking freezes the planet's climate into two radically different extremes. The dayside becomes a permanent oven, where any surface water exists as a superheated sea beneath a thick, steamy atmosphere. The night side is a cryogenic trap, a desert of ice where even the air itself freezes solid and falls as snow. Between them, along the terminator line, exists a world of perpetual twilight, a narrow band of moderate temperatures where the conditions might be just right for exotic, fragile forms of chemistry to persist. The planet's entire meteorological engine is now powered by the stark temperature difference between these two hemispheres, driving eternal, hurricane-force winds that scream across the terminator, desperately trying to redistribute heat that can never be balanced. These opposing hemispheres create a permanent and violent engine for weather. The atmosphere itself becomes a river of wind, a planet-wide conveyor belt desperately trying to even out the impossible temperature difference. Superheated air over the dayside ocean rises violently, creating a permanent zone of low pressure. This sucks in the frigid, dense air from the night side, generating relentless winds that scream across the terminator line. These are not temporary storms, but the planet's permanent state of being, a hurricane-force gale that never ceases. If the atmosphere is thick enough, this circulation can perform a miraculous rescue mission for the night side. The winds carry precious warmth from the dayside, raising temperatures just enough to prevent the entire global ocean from freezing into a single, solid block of ice. Instead, the night side might be a landscape of thick, ancient ice sheets, but with a liquid sea still churning far below. This creates a planet with two faces, one of simmering liquid and steam, the other of eternal, frozen stillness, bound together by a never-ending atmospheric river. Yet beneath this turbulent sky, an entirely different climate system operates in the darkness. The subsurface ocean, insulated by the icy crust and warmed from below by the tidal furnace, follows its own, slower rules of circulation. Heated water from the depths near the core rises, while colder water from beneath the icy nightside crust sinks, creating a vast, slow current that cycles nutrients and warmth through the entire hidden sea. This deep ocean conveyor belt is completely independent of the chaos on the surface, a silent, dark world with its own rhythms and energies. The geology shaped by this dual climate is as strange as the weather. The dayside, with its constant heat and potential for liquid water, would be a world of dynamic erosion and sedimentation. The nightside, locked in deep freeze, would preserve features for eons, a museum of ancient cryovolcanic flows and impact craters. The Terminator line itself, the battlefront between these two worlds, would be a zone of incredible activity where ice melts and refreezes in a complex dance, creating a fractured, unstable landscape of towering ice cliffs and deep, steaming fissures. The geology of this world is not written in the slow drift of continents, but in the constant, rhythmic heartbeat of its orbit. Forget the plate tectonics that shape our own planet. Here, the dominant force is tidal tectonics, a global system of stress and strain driven entirely by the star's gravitational pull. The entire icy shell is caught in an unending cycle of flexure, stretched thin at the points directly facing towards and away from the star and squeezed inward along its sides. This relentless pressure carves the surface into a predictable, global pattern. At the poles of this tidal bulge, the crust is pulled apart, creating deep, long fractures called graben. These are not random canyons, but systematic wounds in the ice, valleys that form exactly where the tidal forces are at their most extreme. Along the sides, the compression forces the ice to buckle upward, folding into vast, sinuous ridges that snake across the landscape. The entire surface becomes a living map of gravitational stress, a cracked and wrinkled face that stares back at its star. This is a landscape with no volcanic mountains or vast sedimentary plains. Every feature, from the smallest fissure to the most massive ridge complex, is a direct sculpture from the ebb and flow of gravitational potential energy. Even the ground underfoot would feel alive, constantly shifting and groaning with the subtle changes in the tidal forces. As the planet's orbit slowly evolves over millennia, perhaps becoming more or less circular, this global stress field would subtly shift. Old fractures might slowly close as new systems of cracks tear open elsewhere, realigning the entire surface to a new gravitational rhythm. The stability of this fractured, ever-changing crust becomes the single most important factor for any potential life. Those deep tidal cracks are not just geological features, they are lifelines. They serve as the primary conduits connecting the dark, warm, chemical-rich subsurface ocean to the frozen, sterile surface above. Through these vents, nutrients from the interior can well up, and water from the ocean can reach the surface, creating localized oases of chemical energy. If the tidal forces were to suddenly calm, this entire system would grind to a halt. The crust would cease its flexing, the fractures would slowly seal shut with new ice, and the vital connection between the hidden ocean and its energy sources would be severed. The world would freeze into a silent, geologically dead sphere. The potential for life is therefore tied directly to the stability of this tidal tectonic system, a delicate balance between the gravitational forces that crack the world open and the internal heat that fills those cracks with the ingredients for life. The window for life on such a world is not open forever. It exists as a fleeting era, a delicate balance between a planet's internal fire and its frozen shell. For life to have a chance, several conditions must align perfectly and simultaneously. The icy crust must be thick enough to shield the subsurface ocean from the harsh radiation and vacuum of space, acting as a protective roof. Yet it cannot be so thick that it becomes an impenetrable barrier, sealing the ocean off from the chemical building blocks that might exist on the surface or in the crust itself. The deep ocean needs a connection to the outside world, and that connection comes from the very tidal fractures that scar the surface. These cracks are the planet's lungs, allowing nutrients to seep down and waste products to vent out. The final and most dynamic ingredient is heat. The ocean must be kept warm enough to remain liquid, and that warmth comes from the relentless tidal kneading of the iron core. This entire delicate system is balanced on a clock that is constantly ticking. The tidal heating that powers everything is not a perpetual motion machine. As the planet's orbit circularizes and its rotation grinds to a halt in a tidal lock, the gravitational stretching that creates internal friction gradually weakens. Planetary engine begins to run down. This means the most habitable period for such a world is not in its fiery youth or its frozen old age, but during a specific golden era in its middle age. It is the period after the world has warmed up enough to melt a vast subsurface sea, but before its tidal furnace has cooled to a point where that sea begins to refreeze from the core outward. Astronomers call this the tidal habitable zone, a concept that adds a crucial dimension of time to the search for life. We are not just looking for a world in the right place, but for a world at the right time in its long evolutionary story. This stands in stark contrast to our own solar system's habitable zone, which is a relatively stable region where sunlight alone can maintain liquid water. For an Earth-like planet, the primary threat to habitability is the slow, billions of years-long increase in the sun's brightness. For a tidally heated water world, the timeline is dictated by the decay of its own orbit and spin, a process that can be far more rapid and dramatic. We must find a world caught in that perfect, temporary moment of tidal grace. The stark difference between these two planetary archetypes reveals a fundamental truth about how worlds work. Our own Earth is a planet of profound geological complexity. Its engine is primarily internal, driven by the slow decay of radioactive elements like uranium and thorium deep within its mantle and core. This radiogenic heat fuels the immense conveyor belt of plate tectonics, constantly recycling the crust, building mountains, and fueling volcanoes. Our planet's thin layer of surface water interacts with a rich mineralogy of silicate rocks, enabling the carbonate-silicate cycle, a natural thermostat that has regulated Earth's climate for billions of years. The Moon's gentle tidal pull does influence our oceans, but its contribution to Earth's total energy budget is minuscule. Earth is a world of intricate geochemical cycles and a stunning diversity of elements and minerals. A water and iron world, by contrast, is a study in elemental forces. Its geology is far simpler in its ingredients, composed almost entirely of two substances, but it can be far more violently expressed. Its entire existence is dictated by an external power source, the relentless gravitational kneading from its star. There is no plate tectonics here, no continent building, no slow mineral cycles. Instead, its surface is carved by tidal tectonics, its interior churned by tidal convection, and its heat provided by tidal friction. It lacks the geochemical diversity of a rocky planet, the rich palette of elements that on Earth allows for millions of different chemical compounds and reactions. This absence of a silicate rock cycle also means it has no long-term climate stabilizer like our carbonate-silicate cycle. Its surface temperature is a prisoner of its orbit and the balance between stellar radiation and its own internal tidal furnace. This very simplicity, however, is a powerful scientific tool. A water and iron world is a perfect natural laboratory. By stripping away the dizzying complexity of Earth-like geology, it allows us to study the fundamental physics of tides, phase changes, and fluid dynamics on a planetary scale. We can observe how pure water and pure iron behave under extremes of pressure and heat, testing our most basic physical models. Yet this simplicity may come at a profound cost for biology. Life on Earth thrives on geochemical diversity, drawing energy from the reactions between water, rock, and air. The limited palette of a water and iron world might offer far fewer chemical pathways for life to emerge and evolve. While its subsurface ocean could be a stable, warm haven, it might be a nutrient-poor desert compared to the chemically rich environments around Earth's hydrothermal vents. The search for these starkly different worlds is not a theoretical exercise, it is an active and urgent pursuit in modern astronomy. These distant worlds are no longer confined to our equations. The hunt for them has become the driving mission of our most powerful observatories. The James Webb Space Telescope is already peering into the atmospheres of nearby exoplanets, not with cameras that see invisible light, but with instruments that read the chemical fingerprints of starlight. As a planet passes in front of its star, a tiny fraction of that light filters through the planet's atmosphere. Different gases in the air absorb specific colors of this light, leaving dark lines in the spectrum, a unique barcode of the atmosphere's composition. For a water and iron world, the most telling signature would be a persistent, unexplained presence of water vapor. If this vapor is detected around a planet that should be too cold for liquid water on its surface, it becomes a powerful clue. It suggests cryovolcanic outgassing, a world venting its internal heat and water from a hidden ocean, just as our models predict. But JWST is only the beginning. The next great leap will come from missions like the planned Habitable Worlds Observatory. This ambitious telescope is designed not just to detect planets, but to see them directly. It will use a sophisticated coronagraph, a tiny disk that blocks the blinding glare of the parent star, allowing the faint, reflected light of the planet itself to be captured. What would we see? We might finally witness the stark albedo contrast of an eyeball planet, a single, dark, liquid pupil of water staring out from a brilliant, frozen sclere of ice. We could measure its infrared glow with unprecedented precision, confirming the exact amount of excess heat radiating from its tidally churned interior. This transition is monumental. We are moving from an era of theoretical speculation to one of actual census-taking. We will no longer be asking if such worlds can exist, but how common they are. We will be able to categorize them, to see if some have thick steam atmospheres while others are frozen solid, to understand the full diversity of outcomes for a world of water and iron. The discovery of even a single, confirmed example would force us to rewrite the textbooks on planetary formation and evolution. It would prove that the universe is capable of creating and sustaining worlds far stranger and more fluid than our own. What other breathtaking, unimagined phenomena might these telescopes reveal? A world with a ring system made of glittering ice crystals, recently ripped from its surface. The faint, city-like glow of bioluminescence in a dark ocean. The possibilities are as limitless as the tides that shape these extraordinary spheres. The planet's behavior defies simple prediction, revealing a system of breathtaking complexity. Its evolution is not a smooth, linear path, but a chaotic dance where tiny nudges can trigger planetary-scale transformations. Consider the strange phenomenon of resonant tidal heating. If this world shares its solar system with another planet, and their orbital periods lock into a simple ratio like 2:1, the gravitational nudges between them can amplify dramatically. This resonance focuses the star's tidal energy into specific, fixed locations on the waterworld, creating permanent hotspots of incredible geological fury. These would not be random volcanoes, but fixed points of relentless cryovolcanic eruption, constantly repaving entire regions while leaving others eerily quiet. The planet's ice shell itself is not a static carapace. As the subsurface ocean freezes or melts in response to the internal furnace, the distribution of mass across the world changes. This shift in the planet's moment of inertia can cause the entire solid shell to become unbalanced. Like a loose skin on a rotating sphere, the entire crust can suddenly slip, sliding en masse over the liquid ocean beneath in an event called true polar wander. The planet's north and south poles could physically migrate across its surface, reorienting its entire geography in a geological instant. The stresses that drive this global slippage also manifest in more immediate, violent ways. The constant tidal flexing builds up immense strain energy in the brittle ice. When that strain exceeds the strength of the ice, it releases not as a gentle crack, but as a planet-shaking icequake. These would be seismic events orders of magnitude more powerful than anything on Earth, fracturing the landscape for thousands of kilometers and triggering colossal tsunamis in the subsurface ocean below. This entire system is fundamentally nonlinear and chaotic. A minute change in the planet's initial spin, or a tiny gravitational pull from a distant moon, could send its evolutionary path veering down a radically different road. One world might become a stable eyeball planet, while another, nearly identical in every other way, might spiral into a steam-shrouded inferno. This inherent unpredictability means that for every rule we derive, nature holds a surprise, a unique world that breaks the mold. Even the planet's iron heart is not a constant. Was it formed from pure iron, or is it alloyed with lighter elements like sulfur or silicon? The composition of that core changes its melting point, its density, and how it responds to the tidal kneading. A core rich in sulfur would remain molten at lower temperatures, potentially creating a more powerful magnetic dynamo, while a purer iron core might solidify more easily, silencing the planet's protective shield. The final state of this world is not written in its ingredients alone, but in the chaotic, beautiful, and utterly unpredictable interplay of forces that govern its existence. The very heart of this world is not a simple sphere of pure iron. In reality, it is a complex alloy, a molten soup rich with other elements that crave the company of metal. Significant amounts of nickel and cobalt would be dissolved within it, along with trace quantities of radioactive isotopes like potassium-40. These impurities are not mere contaminants. They are active ingredients that fundamentally shape the planet's destiny. Each element alters the core's fundamental properties. Nickel makes the alloy denser and stronger, while radioactive atoms provide their own, independent source of heat through decay. This radiogenic heating works in silent partnership with the roaring tidal furnace, supplementing the energy that keeps the core churning and molten. But one of the most influential impurities is also one of the most common in the cosmos: sulfur. Even a small percentage of sulfur mixed into the iron acts as a powerful antifreeze, dramatically lowering the core's melting point. A sulfur-rich core could remain a liquid dynamo for billions of years longer than a pure iron core, which might cool and solidify, shutting down the planet's magnetic shield. This internal geochemistry acts as a fine-tuning dial for the entire world. It decides how much heat the core generates on its own, how long it stays liquid, and how powerfully it can generate a protective magnetic field. Two seemingly identical water and iron worlds, orbiting the same star at the same distance, could have wildly different fates based solely on the recipe of their metallic hearts. One might thrive with a warm, shielded ocean for eons, while the other freezes solid into a silent tomb. This intricate chemistry means that every such planet we might discover will be a unique individual, its history written in the specific elements alloyed within its core. And this brings us to the ultimate question governing all these transformations, a question of simple cosmic accounting. how long can the planet's energy budget last? Its final state is written in the long-term ledger of energy. The relentless tidal heating that defines this world is not an infinite resource. It is a finite chapter in the planet's life, powered by the gradual decay of its orbital eccentricity and its own rotational spin. As these motions smooth out and slow to a halt, the internal furnace that kept the core molten and the ocean's liquid begins to cool. The planet's fate now hinges entirely on where it comes to rest after this great gravitational settling. If its final circular orbit leaves it too far from its star, outside the region where stellar warmth can compensate, the world begins a slow, inexorable freeze. The transformation starts at the boundaries. The subsurface ocean, once a churning abyss, begins to crystallize. The ice ceiling thickens downward, and the floor of high-pressure ice thickens upward, squeezing the liquid layer from both sides. Over billions of years, the entire ocean turns to solid ice, a single, monolithic block encasing the iron core. The cryovolcanoes fall silent, the tidal cracks seal shut with permanent frost, and the magnetic field, starved of its churning dynamo, winks out. The world becomes a silent, frozen billiard ball, a perfect sphere of ice and metal drifting in the perpetual night. Conversely, if the planet's journey ends too close to its star, it faces death by evaporation. The process of photodissociation, that slow trickle of hydrogen escape, continues unabated. With the tidal furnace now extinguished, there is no new internal heat to drive cryovolcanism and replenish the atmospheric losses. The star's radiation relentlessly strips the world of its water, molecule by molecule, over eons. The global ocean slowly boils away into space, the icy shell sublimates, and all that remains is the naked, scorched iron core, glowing dully in the stellar forge. This metallic sphere, a ghost of a once great ocean world, would be a bizarre and rare class of planet, a monument to complete stellar desiccation. The ultimate destiny of any specific water and iron world is therefore a synthesis of its entire history. Its final position, the stubborn chemistry of its core, the initial depth of its ocean, all these factors combine to decide whether it becomes a frozen tomb or a metallic relic. This grand cosmic battle between a planet's internal constitution and the external forces of its stellar environment is one that every world must eventually lose. The temporary, vibrant equilibrium of a subsurface ocean, of tidal tectonics and magnetic shields, is just that, temporary, a fleeting, beautiful moment of complexity in a universe that ultimately trends toward simplicity, toward the cold of space or the fire of a star. Every transformation on this world echoes through its entire being. The tidal forces that flex its iron heart do not act in isolation. They initiate a cascade of consequences that ripple across the planet. It begins with heat, the relentless energy that melts a global ocean and fractures the icy shell. Those fractures become vents, allowing cryovolcanoes to spew water vapor and gases into the void, slowly building a tenuous atmosphere. But that atmosphere is vulnerable. The star's radiation strips it away molecule by molecule, and with each particle lost, the planet loses a tiny, almost imperceptible amount of mass. This microscopic change subtly alters the delicate gravitational balance of its orbit. A slightly different orbit means a slightly different intensity of tidal stretching, which in turn changes the rate of internal heating. The entire planet is a single, breathing entity, a web of interconnected cycles where a tweak to its orbit can ultimately determine the temperature of its hidden sea. To grasp this world, you cannot simply study its ocean or its core or its atmosphere as separate components. You must see it as a single, unified system, a dynamic dance where gravity, heat, and chemistry are locked in an endless, inseparable conversation. This holistic view represents the cutting edge of how we understand alien worlds. We are moving beyond simple snapshots and starting to model these planets as the complex, evolving organisms they truly are. The question is, how can we possibly test such an intricate and distant idea? We cannot fly to these distant spheres, but we can build them inside our most powerful computers. Sophisticated numerical simulations are the virtual laboratories where these theories are tested. Astrophysicists feed equations of fluid dynamics, heat transfer, and gravitational orbital evolution into massive supercomputers. The code then calculates how a sphere of water and iron, subjected to a star's relentless pull, will evolve over billions of virtual years. Will its ocean boil into steam? Will its core solidify? The simulation runs through countless scenarios, each one a possible future for a hypothetical world. This digital experimentation turns wild speculation into a series of quantifiable, testable predictions. We can watch a digital planet become tidally locked before our eyes, or see its magnetic field flicker and die as its core cools. Yet these virtual worlds are only as good as the physical laws we program into them. To ensure those laws are correct, we must crush real matter here on Earth. This is the work of the diamond anvil cell, a device that can recreate the crushing pressures found deep within a planetary interior. A tiny sample of water and iron is squeezed between the perfect points of two diamonds, subjected to pressures millions of times greater than our own atmosphere. Under these extremes, we can directly observe how water transforms into exotic high-pressure ices, or how molten iron alloys behave. These two approaches, the vast virtual universe of the supercomputer and the microscopic, pressurized world of the lab, work in perfect tandem. They provide the ground truth for our cosmic models, constraining the possible and weeding out the impossible. The very fact that we can conduct such experiments forces a profound philosophical question. Are we merely observing the universe, or are we, in a very real sense, beginning to recreate it? These strange water and iron worlds force a profound shift in our perspective. For centuries, we have searched for life by looking for planets that resemble our own, a second Earth basking in the gentle light of a sun-like star. But these tidal planets shatter that Earth-centric model. They prove that the two ingredients we consider fundamental for life, liquid water and a sustainable energy source, can exist in realms we once thought were sterile wastelands. A planet need not orbit within a star's narrow habitable zone to possess a warm, dark sea. It can be heated from within, cradled in the gravitational embrace of its sun. This realization explodes the potential real estate for biology across the cosmos, turning frozen orbits and dim red suns into promising destinations. Our own existence on a rocky, sun-warmed world then appears in a new light. This is where the anthropic principle casts a long shadow. We humans, built from the chemistry of silicate rocks and sunlight, naturally evolved on a world that provides those very things. We are a product of our specific environment, and so we instinctively search for mirrors of that environment elsewhere. It is a cosmic case of confirmation bias. But what if we are the odd ones? What if the universe's most common cradle for life is not a rocky planet in a balmy orbit, but a fractured ice ball with a churning, tidally heated ocean? Around another star, a completely different biochemistry could be thriving in the perpetual darkness of a subsurface abyss. Life there would not draw its energy from the sun through photosynthesis, but from the chemical soup swirling around hydrothermal vents, its metabolism powered directly by the planet's own gravitational furnace. Its entire evolutionary path, its senses, its very perception of reality, would be shaped by a world of pressure, warmth, and eternal night. These possibilities are a humbling reminder. They tell us that nature's imagination for creating worlds, and perhaps for sparking life, is infinitely more vast and creative than our own. Our journey through the physics of one such world is nearly complete, but one final, overarching mystery remains. The ultimate mystery remains unresolved. Despite all our sophisticated models and the compelling story we can tell, we have yet to definitively find a pure water and iron world. Our current understanding of planet formation suggests they are plausible, even inevitable under the right cosmic conditions. Imagine a young solar system born from a cloud of gas and dust that was rich in water, ice, and metals, but strangely lacking in the silicate rocks that built Earth. In such a metal-poor environment, the dominant building blocks for planets would be exactly water and iron, potentially creating entire worlds of the type we have envisioned. The very scarcity of certain materials could force the universe to construct planets from a more limited, elemental palette. Yet for all their theoretical elegance, these worlds have so far eluded our telescopes. Their detection and confirmation represent one of the grandest challenges in modern astronomy, a puzzle that pushes our technology and our ingenuity to their absolute limits. Finding one would be more than just adding a new entry to the catalogue of exoplanets. It would be a monumental validation of planetary science itself, confirming a whole class of world that was once pure speculation. Such a discovery would offer us a pristine natural laboratory, a cosmic testbed where we could observe the fundamental physics of water and iron under pressures and temperatures we can barely replicate on Earth. We could watch in real time how gravity sculpts matter, how phase changes govern global structure, and how energy flows through a simplified planetary body. The search for these hidden giants is not just about finding a new place. It is about testing the very limits of our understanding of matter, energy, and the forces that shape reality. Every new telescope, every refined observation technique brings us closer to answering the profound and haunting question, are they really out there? From a serene sphere of water and iron to a geologically frantic world, this journey reveals a universe of profound transformation. We have witnessed how invisible gravitational pulls can forge hidden oceans in the dark, drive icy volcanoes to repave entire landscapes, and generate protective magnetic fields from a churning metallic heart. These forces can even bring a world to a permanent standstill, locking one face in scorching light and the other in endless frost. These are not gentle processes. They are testaments to the dynamic, often violent, and beautiful forces that sculpt planetary systems far beyond our own. They challenge our very definition of a planet, pushing us to see worlds not as static spheres, but as fluid, evolving entities. Most importantly, they force us to reconsider the narrow conditions we once thought necessary for life. The potential for biology is no longer confined to sun-drenched, Earth-like orbits. It might thrive in the warm, dark abyss of a tidally heated sea, a universe away from sunlight. As our telescopes peer deeper into the cosmos, let this mystery of the water and iron world inspire us. Let it remind us to question our deepest assumptions, to look with fresh eyes, and to always marvel at the endless, breathtaking variety of worlds waiting in the dark. The universe, it turns out, is far stranger and more wonderful than we ever dared to dream.